so there's no students to interrupt the lecture now. Still can't find a bare marker, so you guys are gonna have to bear with me. So, okay. Right. No mind the Jesus there, but sorry. Okay. Oh, there's actually an eraser here. That's neat. But there they have. Okay. So, right. So we still haven't fleshed out the course yet. We still haven't fully fleshed out the course. But I suppose we can start discussing things. So, sets. What are they? What is a set? A set, well, let's make the first definition here. Definition 1, a set is a collection of objects. And the set is, you guys already know what a set is. I talk about sets a lot in the course. Collection of these markers is a set. This entire classroom, if we think of it as one thing, it's a collection of seats, whiteboards, televisions, and lockers. So it's also a set if you think of it as one thing. And that's pretty much it actually for a set. The most prevalent sets in the mathematical literature is the integers. The real numbers, the rationals, the complex numbers, and the quaternions. These are the most prevalent ones. If you're talking about four-dimensional movement and rotation, or four-dimensional systems, this complex numbers are basically our way of solving equations such as x squared plus 1 equals 0, because this over here is x equals square root of minus 1, and we define that minus 1 to be I, complex number, and any combination of this with a real component and a factor of I is a complex number, an element of this. The rationals, Q, are numbers that cannot be expressed as whole numbers, so 4/3 and other stuff like that. 4/3, 5/7, 9/8, those are part of the rationals. The real numbers are, it's a collection of this and this, the integers. The integers are just whole numbers that have their own additive counterpart, or additive inverse, meaning they have a negative version of themselves, so minus infinity to positive infinity. So minus infinity, minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5, and so on and so forth. Those are the integers. And so these are examples of sets. And the important concept too here in our theory is the concept of a structure. So I'm in grade 12 high school right now, but my knowledge exceeds it right now. So let's discuss about structures. Mathematical structures. My markers are not being so hot right now. So let's try rewriting it. Mathematical structures. Mathematical structures are basically locations. We can think of them as buildings. Wherein the structure, well, it's quote unquote structure of the structure or mathematical structure is the rules that dictate what we can do to the elements of the group of the structure. So structure is usually a set, let's say n, equipped with some operator, or called asterisk, that maps, maybe products, arbitrary products of n onto itself. And an example of this operator is the addition operator, where it takes the sum of elements from the set, and then it gives us an element inside the set. If we do this operation onto elements of the set, and the result of applying that operation on the set is inside the set, we say that the set equipped with that operator is closed under that operation. So the integers equipped, God, here we go again. The integers equipped with the addition operation is closed here, and we call this is actually called a group, I believe, or it forms up. That's a magma. This is called a magma. And the basic structure of a magma, the magma is the most basic mathematical structure, and the most basic thing about the magma is that it is closed under the given asterisk or operation that we have. And so this is closed under addition, because if we add two elements inside the integers, like say 1 and 4, or 3 and 5, the results, which are 5 and 4, are still part of it. They're still part of the set. So it means they're closed. It's closed, and it satisfies that condition. And this is something that I'd like to call this is what we call a commutative magma, or commutative mathematical structure, or abelian. People pronounce it abelian, but I pronounce it abelian. We say abelian because if we interchange the two elements in an operation, let's say we have two elements A plus B, it's the same as B plus A. So if we apply this operation on two things or three things, we can interchange those guys, and then it will be the same result. And so that's what it means to be abelian, right? Another example of a structure is the group. Now this is a very important thing, because a majority of the majority of mathematics that we've studied ever since our grade school days or elementary days it occurs inside these things called groups. What is a group? A group is what I said a while ago. It's a mathematical structure. It's a place where mathematics happens, right? It's a place where we do mathematics. Like other mathematical structures like monoids, categories, the magma, of course. We perform our elementary arithmetic in magmas. And it's actually just an integer equipped with, or the integers equipped with the addition operation, the plus minus operation, because it would be also but actually it's also just plus, because we can think of subtraction as just adding by a negative integer. So I suppose we don't need to talk about it that way. So it's just addition. That's good enough. So a group is actually a type of monoid that contains every element contains an inverse. So every element A inside a group, so I'm going to define it now. So a group, which I will call N by this product cross, is a mathematical structure structure such that for all A, okay, for all A inside N, for all A inside N, there exists an A to the minus 1 such that A times A to the minus 1, I'm going to call this dot, it's the dot, is equal to E, where E is our identity element. And also, there exists an identity element E such that for all A inside N, E by A is equal to A by E is equal to A. So we can think of this identity element here, our multiplicative identity, as 1, because, yeah. So every number has an inverse, they have identities. If we have this operation dot that sends products, arbitrary products of n onto itself, we can say there are also rules concerning that, but I'm not going to go very in-depth about that. An example of a group now is the integers equipped with the multiplication operation. If the addition operation, or if the integers with the addition operation is a magma, the integers with a multiplication operation now is a group. So, yeah, it's a group now instead of a thing. Because notice that every number has a additive inverse, or additive multiplicative inverse. And that's basically just the reciprocal. So, we know that 1 is an element of the integers. Now 1 has an additive inverse, 1 over 1. Or maybe something like 2. 2 is an element of the integers. And it has a multiplicative inverse, which is 2 to the minus 1, which is 1 over 2, 1 half. Such that 2 divided by 2, or that's just basically 2 times 2 to the minus 1 is 1. And 1 is our identity element, or our multiplicative identity element. So E is 1 in this case. Now you may have learned in your calculus or your other courses or elementary courses that E is just, it's Euler's number. That's what most people think this E is. But to us abstract mathematicians, we think of E as an identity element that advanced structures contain, like, well, groups here, or magma, or something like that. Majority of abstract objects contain an identity element such that if we multiply it by, or apply it on other elements, we'd get nothing, right? But of course, this 1 here is not an additive inverse, because if we add 1 to any number, we wouldn't get the same thing. We would get an increment of 1 on that number, right? So it's not an additive inverse, but it's a multiplicative inverse, because if we multiply it by any number, we get nothing, because as you guys know from your elementary algebra or elementary operations, any number multiplied by 1 is just that number, right? Well, on the other hand, 0 is an additive inverse. 0 is now RE when it comes to equipping the integers with an addition operation. Because if we add any number to 0, we just get that number, right? So any number A plus 0 is just A. So 2 plus 0 is 2, 1 plus 0 is 1. You guys know that stuff already at this point. So when it comes to equipping the integers with the addition operation, we have 0 as our additive identity, or identity element. And then if it's a multiplicative inverse, it must be 1. If we have other operations that we haven't defined yet, or that's out there and that I haven't defined yet, your additive inverse, if we're going to equip that operation with a set, right, is an element of that set such that if we apply it or if we do the operation on it and then fellow element of it, it does nothing to the element or to that other element inside the set. And of course, it must hold that if we do apply the operation on these elements, it's closed. So the result of, okay, so suppose we still have the same thing, same group, which is, of course, z and our multiplication. Okay. Suppose we have that, and suppose we have two elements a, b inside z. Okay. So I don't expect you guys to not understand this at this point. We've done so much abstraction and generalizing. You guys should get it at this point what a and b should represent. They represent integers basically. And so what we want to say is that a times b is an element of z. So z must be closed. I don't know if you guys can see that. So z must, I'll just explain. So z must be closed under multiplication. So any AB, for any AB inside z, excuse me, their product must be inside z in order for z to be a group. And of course the other stuff. Now, those are a few of what we call the group axioms. And these axioms are fundamental definitions or criteria whether a given structure is a group or not. Now, maybe in your homework I'll place there a couple exercises to tell you guys or to ask you guys whether a certain structure is a group or not, or whether it's a magma or not. So, yeah, that's the basic premise of mathematical structures, and we're going to treat femboys now. We're going to treat femboys and other members of the community as structures. And when we treat them as structures with elements being their characteristics, we get to do some pretty wonky things. Such as, well, in my Stephenson-Maxwell paradox video and our Kirov-Argyll paradox video, we prove that if we treat a femboy as a group with the elements being the characteristics, the group itself becomes independent from one of its constituents. So what I'm saying is that we can essentially remove or extract. We can extract, or we can say that a given set is equal to itself without a certain element. So basically, we can extract an element from the group and then say the group is still the same thing and that it has no effect, or extracting the thing has no effect on that structure or that group. So I need you guys to really understand what structures are before you guys study this course, because we're going to be discussing about them a lot, and of course their underlying axioms and assumptions that make them what they are. So I believe that's that. So next video, I suppose we're going to start abstracting things, and yeah, apologies if this video is a bit short because we're a bit short on schedule. I know I arrived early, but it's still my school. I'm in school right now, so yeah. I don't even know if I'm allowed to do these lectures here. So, yeah. Mathematical structures, important thing. See you guys in the next lecture.